site which is surrounded by many stakeholders, what we call stakeholders. They may include a party wall. We might be digging next to a big party wall, belongs to somebody else. So we might be digging next to that, 10 meters deep, 12 meters deep, 15 meters deep and so on. So these are all the stakeholders, and these are also the third party. So if you're actually developing a big site in London, Victoria, or in other busy places, surrounded by streets, all those streets have got major utilities. London is a connectivity of, infrastructure that is horrendously occupied, very densely sort of populated with the pipelines and gas and BT and old tunnels and the Royal Main tunnels and disused tunnels and you name it, everywhere it is there. So I think these are all the stakeholders we need to interface. Sometimes even above the ground, you may have railway embankments. You may have abutments, you may have viaducts, the trains, and they all belong to network rail. So again, if we are actually doing something at the ground level here, digging down to this level, so at that level, there may be a viaduct foundations, there may be railway next door. How do we deal with all those? How do we engage with these people? What should we look for those things? What are the things that we need to be looking at in terms of acceptance criteria? What is acceptable for them? If you go and tell them, I'm going to dig next to your basement, nobody's going to like it, right? So they want to know what is called risk assessment. So we actually talk about risk assessment and interfacing. Those are the three topics. We spend roughly about an hour on each of those topics. You can stop me anytime you like. The objective is to understand that whatever we are trying to present here. And the day 2, which is next Monday, I touch again 3 topics. One is methods of construction. So there are various ways of building this basement. Okay, it's a single story, 4-story, I've done a 6-story basement. So whether we do top down, so everything right, and we do bottom up, so we dig everything and move up, or we could do hybrid, somewhere between this and that. Yeah? So those are the 2 types of construction I talked about. Why should we go for those things? Can we dig all this here and then build from the structure from here? Or can we put the roof first and then dig below that? Yeah, that's called top down. And then also suitable props. So how do we actually hold the ground? Obviously, if it is, as you say, 12 meters wall, it's not going to stand up. So you've got to hold it. So by means of some props. Yeah? Because otherwise everything will fall in here. So those things we have to talk about. And then I also talk about observational approach. What is it about? What do we monitor? How do we get the confidence of the people who are relying on us in terms of stakeholder assessment, third party stakeholders? We need to ensure that we gain the confidence, because if they go and say, look, you've made a crack on my building, and that's it, the contractors are stuck. They can close the shop, because they know that they will be after you. If you have a small crack occurs on your party wall, you will not be happy. And if there is a lot of very big apartments, whatever they are very expensive stuff, they may say, oh, then a crack has come because you dug next door. So can you come and pay for this? And that is going to be a big issue. That is why it is very important we have observational approach. We give them confidence. What are we monitoring? We tell them. We keep everybody informed. We should say, look, we've actually, before we started digging, we are taking the readings now. We're going to dig and monitor, and then we keep informing you what is happening. And that's very important. Keeping everybody in the same place. Keeping everybody informed what is happening. Make sense? Yeah? So that's called observational approach. The way we organize this sort of course is theory and case studies presentations. And then there will be a small tutorial, as Subhi said, because the objective is you must know what you should look for. If somebody comes and says, I got a big space here, I want to dig 3 stories, 4 stories, 5 stories, but I'm next door to a railway line. Yeah? So these are the case studies. What should you be looking for? What should you be advising your client? What should you be looking at in terms of your risk assessment? What should you be adapting in terms of your solutions? What should be the method of construction? How do you actually advise the contractors to dig it? How do you actually design it? So there will be a tutorial exercise which I will cover. I will tell you, I will give you a simple set problematic, a very, very practical problem where I'm doing about half a dozen basements in London. So those things I'll just set, and then I want you to understand, come up with your risk assessment and say, look, this is what it is. So this is a simple tutorial exercise. It's not going to be very large. Should be spending more than about a couple of hours in my view in that. Okay? And of course, I always welcome feedback reports. It is very important for us that you give us the feedback. Okay? Right. So, Right, retention system. So, right, no, so some client comes and says, I want to build a 6-story basement. 6-story basement. So, the challenge, first thing is, what method of retention system that we should select? And sometimes, in London, most of the properties in London have got one-level basement. So you got another challenge. That means, if you are ground there, and you only got a wall there, that is basement wall, which is roughly about a basement. And the client comes and says, I want to put a 6-level car park, and gym, and a swimming pool, everything in below, which is what we've done on the hotel buildings. And now we have to start digging from that level or this level, we have to think. Because remember, we still have a basement that is already there, and we are working in the basement. We are deepening the basement. So, what should we choose? What retention system should we use? So, there are various types of retention systems, which is the continuous piles, which is a hard, soft, and there are 2 types of things. I will tell you about that. We've got a secant wall, secant pile system. We've also got a king post system, we've got diaphragm walls, and we've got steel sheet piles. So those are the main systems in which we build our basements. So if you look at the continuous piles, what you have is basically a series of piles. You do hit and miss. So basically, you put the pile rig there, or pile rig at the lower level, depending upon what the size of the pile rig is, you start digging next to that existing wall. So you start building, because you want to deepen the existing basement, if you have one. Otherwise, you drill from the top. So you start putting pile, right? So you drill, there are various methods of piling. So you can do boring, you can do CFA and all that. So these walls are to throw why do we use gaps here, do you think? Remember, if we are actually dig these piles from ground level, why there are gaps? Why should I leave it? Why do you think? What happens between them?
Not possible to close the another pile?
Possibly, but why am I choosing continuous pile? What am I trying to do there? This is all ground, yeah? So we're going to drill this pipe, come back and drill that pipe, come back and drill that pipe, hit and miss, yeah? Come back and drill. So in between these two, the soil will hold it. Yeah? The soil is still here. So when I'm drilling this pipe, when I do that pipe, come back and do this pipe, between those two, the soil will arch. So I'm making use of the ground that is good, it can arch, and assuming there is no water on this side. What happens if you got a lot of water? Everything will, you can't work, right? So, contiguous by its own meaning, you can see if it is very dry environment outside, there is no water, and you want to save some money, and you want to make sure the soil will arch nicely between the piles, yeah? So what you do is you simply pile from there, one pile, one pile, one pile. You try to keep the spacing, not leave enough, not too much gap, because obviously you've got to make sure the soil is good enough to arch between those two. Yeah? So remember, we are digging on this side of the pipe. So that side there is earth pressure, right? So that earth pressure will push. The water, if there is water, it will push. So we don't want too much gap between them. So we try to keep roughly about 300 to 400 millimeters space between them. So that we can see, basically, we start almost 150 centimeters. And then in dry stable soils, these are very efficient because you are relying partly on the ground. You drill it, and then you put a tremie pipe, put the concrete, lower the cage, take it out, the job done. So the concrete sets, and then you hit another one, and then you come back and do this one. In between, the ground is doing the work for us to hold it. Yeah? So now we start digging. So you can start on digging on our side. This side is very low potential. So the contiguous piles, we use them on a very large basements where we think water, I mean if you hit water accidentally, you are stuffed. That's why it's very important you have a proper ground investigation, proper groundwater table recording, ground monitoring record, groundwater monitoring record, all those records you must have. Because what you don't want to do is when you start doing from the ground level, let us say you're digging 20 meters, now you're going to excavate bit by bit, right? If you go to 10 meters, you don't want water to gush through this. So you've got to make sure absolutely dry, and if you find it, we do find sometimes, there are perched water tables which we can never estimate. We talk about a large size, let us say 50 meter by 50 meters, 10 times the size of this room. Yes? So what happens is, we don't know where the perch water table could be in one corner. Yeah? So what will happen is, if we get into that sort of problems, we try to go down to lower level and we plug the water. Sometimes it could be an issue, sometimes it could be, it depends on how much water is coming through there. But in reality, this is a good system if you use nicely in a dry soil where you think water is not a problem. And you can see the spacing of these piles, 1.1 to 2 piles diameter. So if the pile is 600, I'll try to keep between 600 to 1200 or 10%, which is about 1.1. So these are the things that we choose. So the diameter can be anything. The minimum rig can do is 450. I'll show you another slide where it actually shows what sort of limitations of these rigs are. So you can do a 450 diameter, you can do 600, you can do 1200. So it's as massive as that. Yeah.
I've seen continuous piles but with the capping beam on top of it.
Yeah.
What's the use of the capping beam?
Yeah. Sometimes what happens is, it's a very good question. In the urban environment, again, when we have a box, it is so inevitable that end columns will land on the border line. So the columns that are carrying the superstructure, whatever 10-story, 20-story, 100-story building, you will see those columns will come and land on the line of the border. Because obviously client wants to maximize the space. You don't want, if the column, imagine this is a column coming from the top down to there, you are losing the space. So what I want to do from the client point of view, I put a capping beam here all around. Imagine this room is a basement. I put a capping beam and I land my columns directly on that. So that way, client is getting maximum benefit. Yeah, and they are also taking vertical load in this case. They are not just only there to hold the ground, but they are also taking vertical load because the columns are transferring the load vertically. So the capping beam helps to distribute the load. Do you remember the grid of the columns is roughly 8 meters, 10 meters, 15 meters, whatever. So if you got a column there, if you got a column there, you want that to be distributed nicely on number of piles. So because that way we put a very rigid capping beam. Okay, so that's the reason we actually put a capping beam. So we know more about contiguous piles now. I think that's again, the depths can be anything. You can bore it 40 meters, 30 meters, 50 meters. But if you are using a CFA auger, you've got limitations. So there's this continuous flight auger that goes only 26 meters. But if you are boring, you can bore whatever depth you want, yeah, and then stabilize the hole and then move on. So that's the contiguous piles. The next one. So this is one of the contiguous piles we have done in London, as you can see, surrounded by all sorts of buildings. Next door, very close to the building, as you quite rightly said, there's a big capping beam, because that capping beam there is what is carrying the building column load onto it directly. You understand? So that's the capping beam. And then that is what we are digging about 13 meters here from the ground level. So this is a series of piles. We start at that level, operate the pile rig to do actually all the piling, construct the capping beam and start digging down and then build from bottom up. So this is actually, you can see clearly we created the whole big hole in the ground, started building from bottom up. Yeah? So that's one of the things that we have done. So the next thing is the secant part. So there's a slight variation between this and that. So the secants, what we do, first we do what we call primary piles. So the primary pile is this one. And that is done in a soft concrete. You could have two different types of it. If we take a bentonite, very soft mixture. The reason that we want the soft mixture is because we do that and we hit and miss, we do that one. The idea is to interlock using a structural pile between them. So if you got very hard concrete, it's very difficult to break it. So that's why you want to put a soft concrete in there. So again, we do piling there, hit and miss, move to the next one, do the other one, and then push that pile, and then put the cage over the concrete and take it off. So now you got an interlock here. We want to make sure there is enough interlock at that point. Otherwise, what happens? Yeah, it's a swimming pool. Yeah, if you got to water, yeah.
If you're drilling clay, the interlock, you can get like a residual of clay between those interlock there. So
Unlikely, maybe there is a little bit, but unlikely. The reason is, we want to make sure there is enough interlock between the concrete itself, the auger itself when it is cutting. We want to make sure there is going to be enough cutting through the concrete, and then there is enough. It's very unlikely that you will find that as long as you maintain the verticality of this, so how it is actually going, and then the other one comes there. So if it is held like that, then there is no interlock, the other pile, so you got a gap. So we want to make sure at every depth, especially deep pipe, if you go for 4 meters, 4 meters, 12 meters, 4 or 6 meters, 20 meters, whatever, by the time you go to 20 meters there, that pipe is supposed to be like that. It will be, and because you are driving from here, it may end up with like that. And then when you do the next one, that may end up like this. And you do the middle pipe, there is no interlock, is there? So we want to make sure the tolerance control. I talk about the tolerances also. What are the tolerances we can achieve? What depth? How do we ensure that we have enough interlock so that the water cannot go through there? Obviously, this is very important. You can see there is water there. That's the best way to control it. An advantage, here again, the reason is called hard soft is because we want to keep this as a very lean concrete, bentonite cement mix, so that we can nicely push the other auger, cut it through, nice bond, concrete done, job done, start digging. Fine. But we also use the variation of that, it's called hard. So the hard, what happens there is, you can see the difference between this and that. We are actually pushing a steel cage in there, reinforcement cage. That means, if there is with this scenario, these are sacrificial, yeah, because they're not structural. They're simply there to just hold the ground, hold the water, a little bit in temporary condition. But in reality, the pile that is working structurally is only that. So the spacing is very important. If the spacing is maintained, you can see the stiffness of this wall will be less compared to the stiffness of this wall. The reason for that is now that is also structural. So we do put a bit of concrete there, but not very lean mix, but we can cut through. Well, obviously we don't want to put a 40 Newton concrete there because it will be very difficult to drill through to make a plug. So we put a concrete that is strong enough to hold that as if everything is a wall. So structurally, this is more efficient. So why do I go for this one than this one? What is the reason? Why do you think I should go for this than that?
Side strengths.
Side constraints, yeah, very good one, yes. What else?
Very cheap. It's cheaper the first one.
Yes, it is cheaper, yes. That's what's another, yeah. But think in terms of the ground. What happens to the ground? If I got space, I can put a very large diameter, let it hold. If I got space. Remember, client borderline, client legal line is there. Yeah? More you come into his space, less rentability he is getting. Yes? So, what happens generally is if you want to use that system, if you are doing a 20 meters basement, let us say, you may end up with a very large diameter pipe. So that means you are occupying, that is the client side, is the legal boundary, you are occupying more space in there. If I want to make it structurally efficient, I will use a thinner pile, make the whole wall structurally efficient, hold the soil like a nice wall. Everything is continuous. You see what I'm saying? That is the reason we go for both. So obviously, as you quite rightly said, that's more expensive. But it will save a lot of time, money for the client. So that's one secant wall, as you can see, next to Thames River. Yeah? No wonder we have to choose because the water level is very high. You can still see a bit of seepages. That's because our interlock is not extremely good. Because of the tolerance, because the positional tolerance of this one, you are doing from ground level, that is the bridge, that's Westminster Bridge. So you are actually doing piling from that level. So sometimes you lose a bit of interlock, so you get a bit of wet patches. But you can control it at least. The rest is all, you can see, is all fully dry, and then we are digging next to that, and then we dug. This is again a bottom-up construction. Again, this is actually, we are talking about 14 meter deep in this case. You can see clearly again a cabin beam that is being built with the props and all. We'll talk more about the props later on. So again, the piles in secant walls, the spacing is about 0.2 to 0.89 meters. That's the sort of spacing. The important thing is to ensure you have enough interlock. Remember, you are going to work with a water body. If you don't have interlock, it's a swimming pool. Yeah? So it's absolutely unsafe to work in that condition. So we've got to make sure there is enough interlock between those things. So this gives you some guidelines in terms of what is the diameter of the casing, what is it, sometimes we have to put the casing, sometimes we have to put temporary casing, sometimes we have permanent casing. Why do we need a temporary casing? When I'm doing the piling, why do I need a temporary casing? Can I just drill the hole?
If the material around it, like
Absolutely right. Absolutely. So the
maintain
pile
the-
collapse, the ground, as soon as you make a hole, imagine if it is a gravel or a sand, what will happen? Simply, it will come in. So there is no way that you can say that I am going to pour concrete and it's going to carry load. So you got to put a temporary casing. Sometimes we put a temporary casing size. So you can see if you take a diameter of 1000, casing size is 1000. This is a case, secant case CFA, continuous flight auger, and then drilling tool is 900. So you drive a meter diameter casing, you put an auger in there, and then you drill it 900. So you can see the ground is not collapsing, and we are actually, when we withdraw the auger, we pour the concrete, we know definitely a 900 diameter pile is made. Yeah, make sense? Everybody clear on that? So this just gives you sort of thing. Sometimes we use segmental casing. Segmental casing, why do we use segmental casing? Why? Why can't I just use single casing?
When it's too deep.
Yeah, absolutely right, yes. If it is too deep, I can't bring this one 26 meters long, hold it up in the air and bring it. I can't do that. It's too high. And then working in a sort of a conditions like that is very difficult. So what we do is we bring in pieces like this. Small pieces, attach another one, and keep going all the way to down wherever you want to go. So that's where it is important that we use segmental casing. As you can see, there is a relationship between those two. That's what we use. Make sense? Great, very good. The other method that we use is called diaphragm walls. So what do we do in diaphragm walls? I mean, this is actually, as you can see, taken from dashes. We have a very big rig with a drilling tool here. So it's a grab. So what we do is we put a temporary structure on the ground. This is just what is called simply a guide beam. So for the guide, because you need to know where you are putting the wall. So you need to have a guide along both sides. Suppose you want to build this wall 20 meters down, you need a guide wall on both sides. So you put that as a guide wall, you can see the guide wall there, guide wall at the back. The rig actually grabs, so that it goes, then it takes the material, comes out. But how do I stabilize the ground? You've taken the earth out of this in the ground, yeah? How do I stabilize the ground? Absolutely right, yeah. So we got to put something, a chemical or something, to hold the ground. Because we are talking about very large diameter. I am looking at a project where diaphragm wall, we are talking about 1.8 meter thick. Yeah, is almost as high as. So that is a sort of thickness. So you are actually talking about that sort of thing, grabbing and taking out. That's the thickness of the wall we are talking about. So that's this thickness. So to hold the ground, we got to pump bentonite. That's why you got bentonite plant. And then, so we pour the bentonite, and then they got a concrete pump there. You can see the concrete pump cage we inserted, taken that out. So you grab the earth by using big grabs, take it out, push the bentonite, and use the concrete, lower the cage, and then simply bentonite comes up, treat it and reuse it and so on. Make sense? Yeah? So that's the diaphragm wall. Now, when should I use the diaphragm wall? When do you think I should use the diaphragm wall? Yeah?
Tunneling structures.
Yeah, absolutely, yeah. Yeah, and also, if this is very deep, the rigs have got, when you are boring, it's very important, when you are working in a water strata, it's very difficult to see how you are going to get an interlock. I am looking at half a dozen jobs where I have to dig 70 meters for a shaft. 70 meters. Yeah, this is one of the HS2 shafts. So 70 meters. How do I know at 70 meter depth I got interlock between the piles? Remember, I'm going to dig, and I know it is water bearing strata. So you can't take any risk. So the advantage with this one is you get a better interlock, you get a better control, you get a better installation tolerance. Yeah. So that way I can know by the time from the ground, when I dig down to 70 meters below, I can see the interlock between the panels. These are argument panels, you can see that's 2, 3, 4, and then you come back and do the middle panels. Yeah. So you do that hit and miss. And once it is, I know when I am at this level, minus 70, I know there is a good interlock between them and it's all dry. I can start working at this level. Make sense? As you can see clearly, to rise a 70 meter cage is not going to be easy. Yeah? Because this wall, we are going to pour 70 meters. And again, you have to think about what is the volume of concrete that is going. Because in London, there is a restriction. You can't do 24-hour operation. Some of the times, we may have to go for a special permission to get 36 and 48 hours of operation. Because if you look at the panel, I have to pour full panel concrete volume in there, right? So that may take probably 48 hours. So you got to go take permission. So you got to choose the length of the panel in terms of your deliveries, in terms of approvals, in terms of whatever the council is telling you, you can't do more than 24 hours routine. Yeah? So the other thing is also, you can see that cage that he is dropping here is 70 meter high, up in the air. Yeah? So it's 70 meter, you are holding it and you are dropping it to the ground. So there's going to be a huge health and safety operation. Yeah.
I would like to ask, for example, when we are digging, how we can check we are digging it vertically?
Yeah. What happens is, in this one there is an instrument here, in the grab itself. It will tell you on this guy's machine how it is actually going. So they can control. There is a bit of a play in those things, so they can see better control. Yeah. So yeah. So this is all the operator can see what is the grab doing this or there. When he's doing the grab, so the grab is going like this, it's going like that. He's able to control that a little bit. So that is why, and because it's such a big grab, he can control it. And you can see clearly that the issue here is that cage, even if you use a minimum steel, we're talking about lifting a 35 ton up in the air and dropping it in the air. Yeah? So these are all the things that you have to think about, again, in terms of the reinforcement. How do I fix the reinforcement? Why do I have to put the reinforcement? What happens if I don't put the reinforcement? Yeah? Yeah. So it's a plain concrete. You're going to dig next door. So the plain concrete wall, it won't span. It's simple. So the concrete will not span. If that is one floor, that's the next floor, that's the next floor, next floor. The wall has to span in temporary condition from there to there, right? Because I'm going to dig from ground level to the next ground level, next basement level. So it has to span, so it won't span. Even if you put 2 meter wall, it won't. You can put probably 4 meters as a mass concrete, but the client will say, I don't have space. Yeah? Makes sense?
You said that you pour, it's like a 48-hour job, 4 sessions. But yeah, for 38 hours you have on the job, when do you put the coal joint? Would you put it at the top or bottom? You have to pour.
Well, you can't have a cold joint.
You can't have a coal joint. So how do you end up?
Yeah. So what we do is, in the grab size, you can see the grab size here.
Yeah.
The grab size varies comes in multiples of 2.4 meters. So if somebody says, no, you can't pour more than 24 hours, I will only do a panel of 2.4. If they say, I can do 7.2 meters, I do one grab in the center, go to the other one, another grab, that side, another grab. So I open 7.2 meters, then pour concrete there. The other thing is also important, again, you as a geotechnical engineer should know that if you open a very large hole, although we are putting bentonite in the hole, if you got next door a great listed building, you will have to still think about what is the movement in temporary condition. Because that 7.2 is almost one. So it's about this size, yeah? This is the panel. You are opening ground 1.8 meters, it's about that. It's like a trench you cut. And next door you have a building. So they will be worrying, they will be asking, you got a bentonite which is less dense and lightweight, lighter than water and so on. So you simply fill the water. So what is the ground going to do? Ground is not going to sit there, it's simply going to collapse, isn't it? It's going to move. Because you restrain, your horizontal strain is 0 at the point of hole. So it's going to relax. When you're going to relax on the ground, when you temporary condition, it's going to move the structure there. So you got to think about these things. What is the movement during installation of diaphragm? This is very important. As the bigger trench you open, more movements will come. Yeah? So this is a diaphragm wall construction. So that's one of the diaphragm walls we've done next to Houston Road, as you can see, next to the canal. The diaphragm wall. Those panels are 7.2 meters thick. We've done 7.2 meters. And you can see that's actually about 13 to 14 meters deep. And these are the props, and again, this is a bottom-up construction. So we actually installed the diaphragm walls all around the site, as you can see clearly. You can see the fantastic interlock that we got. Obviously, between the joint, when you do the panel, that's one panel, so you got one panel there, got another panel. Between them, there is a water joint. So that is also nicely interlocked. So the water cannot come through. So it's next to the river, you can see how dry it is. Yeah? So that's the beauty of the diaphragm walls. But you will see soon, it's very, very expensive. And it sanitizes the site because you need bentonite plan. If you're talking about 1,000 meter, if you're talking about a pile, concrete, or let us say in that panel, the concrete that goes in there, remember it goes to another 4 or 5 meters below the excavation also. We're talking about, let us say, 300 meter cube of concrete. That means you need 3 times more bentonite. That means 1,000 meter cube of bentonite I need on site. So I need space. It sanitizes the space. It's occupying a lot of space. I can't do anything else until I finish all that and remove the bentonite plant. Yeah? This is what I'm saying? You have to think about those logistics also. What are we putting on site? So that's the diaphragm wall we have done. You can see clearly how best interlock can be achieved even when you are working next door to water. Yeah? Right. This gives a summary of what diameters we can do, what sort of weights we have to think. Because if you talk about a diaphragm wall, we're talking about that kit being 120 tons. So it's a massive kit. It's standing there. Remember, we are doing from the ground level, yeah, and where the ground may not be good enough. So you may have to improve the ground, even in temporary condition, to take that load. So what we call piling mats. So you got to build some stuff. When you do the demolition or whatever rubble is there, you need to bring that and make sure that the stability of the piling rig or the diaphragm wall rig is not at all compromised. Because remember, we're doing very large operations. If it falls, it's going to. There have been cases where the whole rig fell onto the railway track. Yes. So stability is very important. So the piling mat, the mat that is going to sit on in temporary condition, you have to think about what sort of pressures we are generating under the tracks and what material we need to put under the tracks before you start doing anything. So this gives you an idea of the ton. And then again, if you got a full displacement pile, we talk about 90 tons, and you can see the diameters and the depths we can go. You can see the diaphragm wall, you can go up to 80 meters. That's the sort of range. Yeah? And this one you can go to 21 meters. Screw displacements is about 20 meters. And rotary drilling, if you are actually drilling by rotary means, you can go as much as you want, 75 meters. We are doing in London 80 meter piles by boring. So you keep boring. Yeah? And then sometimes you have to use a temporary case. When you go into hard stratum like London clay or something, it will stand up on its own. And then now we are able to send a camera and look at the hole, look at the collapse of material into the ground as well. So that way we can control it. But mostly you'll find temporary casing is only used in the top layers to hold the ground. And again, you can see the maximum tonnage, in terms of what is the kit that we are using. It's a massive kit that we are using. And then in the CFA piles, you can see maximum 32 meters, minimum diameter 350, maximum you can go up to 1200. And then if you are using a cased CFA, you go minimum is 600, 1000. And again, you are limited by that auger, which is the length of the auger that can go 26 meters. Can't go beyond that. Again, you have to think about the headroom heights. So this, remember, we have 26 meter auger is standing there, so you need enough headroom. Sometimes we came up with a low headroom rigs also. Sometimes we have to work in the basement with 8 meters rig. There are very expensive rigs that can bring. So you can screw the auger as you can attach a 8 meter auger and then put another one and then keep going down. If you got a low headroom height. Yeah? But if you got full headroom, they will bring all 26 meters and they start pumping, pushing everything. So these are the sort of range. It gives you an idea of what diameters, what load ranges, what sort of lateral forces it can take in terms of that. The other means is we use what is called sheet piles, steel sheet piles. Why should I go for steel sheet piles? I think. Why steel?
Is it good for temple? Is it good for temple?
Yes, they have been used in permanent condition also, but yeah, mostly they work in temporary conditions. Again, I think with the sheets, installation wise, you have to think about whether you can really push to the ground. Remember, the sheet is taken. The sheet is about that wide, yeah, and that sheet is held by the machine and you push to the ground. So you got to think about what sort of ground we are pushing. If it is gravel, it will go like this, yeah? You're pushing it through the, if you're pushing a sheet through the gravel, what will it do? It will do like that, yeah? And it will go like this. By the time you dig it, you can see the wall is like that, yeah? You don't want that. And sometimes it could be hard rock, sometimes it could be very stiff clay, so it's very difficult to push. Remember, we got to put a lot of torque and force to push through the, overcome the friction and push the sheet. This is Victoria Street, London, Victoria. So what we did was actually, the engineer scheme was to use a secant pile. This is Victoria Street, main Victoria Street, the Victoria Station is there. So we said, we looked at the condition of the, our geotech guys looked at the condition of the ground there. They said, we can push the sheet, it's not a problem. And we did that. You can see the sheet piles are used instead of secant piles. The beauty of that is, you can see the profile of the sheet is like that. So you push that segment, and you push the other segment, that gets interlocked there. So you keep pushing one after another, yeah? And that way, you form a big basement. Again, you can see here, this is the bottom of construction, next door to Victoria. The speed of these sheet piles is extremely good. The cost is also relatively, in terms of the sheets, it's much cheaper. So that is why I think we said, let's go, it will save a program, and it will also save you cost for the client. And also, you can see the depth of that is generally no more than 450 millimeters. We talked about temporary conditions. Sometimes we can use that as a back shutter for pouring concrete. So what we did here was, we used that as a back shutter. So you put a front shutter in here and pour concrete. That becomes a nice wall. So this wall is like a wedged wall. So the stiffness of that wall is very high. Yeah? So you get a much more stiffness. You can make use of the sheets in temporary condition, permanent condition. What is the disadvantage in the sheet pile? If you got water that side, what happens? Yeah. So if that interlock is broken, again water will gush through. That's number one. So what we do is sometimes, as we go down, we put a flat plate and weld at the joint. So this is called clutches. Those clutches get welded as we are digging. So we push the sheet, another sheet, nicely interlocked like this. As we dig in front of it, we put a flat plate and then we weld it. So that's called basically welding the